Satvik is the only child of their parents and was brought up being over-pampered. He was born in Andhra Pradesh, India. He did his schooling at VP Siddhartha Public School, located in Vijayawada, India. Later, he chose the biology stream during 11th and 12th grade and completed his Bachelor's in Dental Surgery, that is BDS degree, in 2012 from Sibar Institute of Dental Sciences, India. To further advance, he went to the US. Interested in pursuing translational research, Satvik completed his master's degree in 2016 from Rutgers Graduate School of Biomedical Sciences. Later in life, Satvik wants to establish himself as an independent researcher back home. To reach his goal, Satvik later pursued Ph.D. at Rutgers School of Graduate Studies, focusing on Duchenne Muscular Dystrophy associated cardiomyopathy. Currently, he is working as a Postdoctoral Fellow under the guidance of Dr. Dominic, understanding the role of various transcription factors regulating cellular metabolism in stressed hearts.
Thank you, Dr. Satvik, for accepting my invitation at Eclectica, and I welcome you once again. So I think it will be a very interesting conversation that we will be doing right now, and I think it will be a very insightful one as well for all our audience here. Thank you once again for being here on the show.
Yeah, it is always happy to share a journey because I always see that I have gone through a lot of ups and downs and a lot of mockery also during the initial stages. So I felt like sharing the journey would at least encourage someone who is having a similar passion. So that's one thing which I, as soon as you approached, I said yes, because it would help someone at least. I'm not aiming for 100, even if one person is able to, if it gives an encouragement to at least one, the number starts. So, yeah.
Absolutely. I completely agree with you. So, I mean, your journey is very interesting, and that is how our show is named today, like from tooth to heart. So, my first question would be like, what exactly was your inspiration? Like, what inspired you to make this transition from dentistry to cardiovascular research, and how did you, make this switch altogether?
So, the thing is, basically, I had great interest towards research right from the beginning. Since my schooling. After my 12th grade, I was really moved with Mendelian genetics, I would say, based on the professor who taught me. I guess many of you guys know that there is a lot of peer pressure at that point, and I was being asked to choose only like healthcare stream, and out of which I got a dental admit, so I joined a dental school. But however, my passion towards research was slowly growing on. I attended like n number of conferences, and especially one conferences which I attended in my second year. I didn't meet in, but the keynote speaker, he said like less than 0.5% of the dentists do research. Mm-hmm. So that really encouraged me, and it boosted my thoughts like, okay, there is a really great need for research at least. And personally, from then, I started to have a great interest towards stem cells when I came across pathology. And from then, I thought like, oh, people try to have a lot of issues with tooth, like many lose their tooth. Why can't we regenerate tooth? So in 2011, I had a thought where like creating a tooth-like scaffold, because at that point, we had 3D CAD CAM imaging and others, by which you can proportionately design a tooth according to your dimensions on the other side of the jaw. I tried to create a rough scaffold. It's more like a hypothetical thought at that point. And after a great fight with my parents that I want to do research, and my faculty at Sibar, where I did my dentistry, they really spoke with my parents and said like he has great potential towards research. That's when the journey started. And before doing that, I'm sorry, I'm giving a lot of intro at this point, I guess.
Oh, so, it's very interesting. It's your space today. So we are here to hear from you.
Yeah, so then I initially tested, am I a good fit to research? So I did volunteer as a guest researcher at CCMB, which is one of the finest institute in Asia, I would say.
Absolutely.
And there, that is like learning ABCD in research for me. Like I never handled a pipette where I did it for the first time. The first exercise I was given is aliquoting milky water in Epindar's. So
Understand.
that was the first thing, and then slowly over the time, the research JRF at the institute, he said like, okay, I'll give you two dishes. Why don't you isolate RNA from the stem cells? And that was a stem cell lab. So that was I was really lucky to work on stem cells in the volunteering itself, and I got really good purified values. And he said, okay, do the rest. That was like a biggest acknowledgement for me and encouragement. So then I thought like, okay, I can go ahead. During this journey, one of the best guide I got was Dr. Ranganathan. So he is my go-to guide. He has done BDS, MDS, and he's from actually Ragas Dental. He's the HOD of oral path at Ragas.
Yes.
And he later did MS Oral Biology at Ohio State, which is a pretty good university. And later on did PhD back in India at Tamil Nadu. So he, whenever I felt like, can I compete with these MSc graduates and other, then he said like, see, you are already a doctor where you have learned a lot of skills. Now you're trying to like correlate few other things. So you are definitely way ahead. But only thing is you need a lot of experience. So then I thought instead of directly moving on to a research, why don't I study the background? So I did my master's where I got an admit at Rutgers. Followed by that, I did my PhD. So during masters, I gained a lot of maturity. Actually, in masters, I did masters only to do stem cell biology research, and with having one of the passion as 2-3 generation at that point. And this was in 2014. So when I came to US, when I was like searching for people for so that I can apply for PhD, I came across one professor at Columbia where he published a paper stating he regenerated in mouse the tooth.
Awesome.
And that paper was published in 2012. So then another encouragement for me was, okay, I got an idea in 2011, which is like close enough to someone, a great expert in the field. So I felt like at least I'm matching their thought process. So I'm okay for research. That's where I was slowly building up my confidence. And when I joined in masters, I was mainly, I did like 3 rotations in my masters. So I was start doing volunteering right from day one. So during that, one of the professor I worked was working on mitochondria, which is going to be the powerhouse of the cell in regular terms.
Right.
She was mainly working on a protease in the mitochondria.
Okay.
So she is highly enthusiastic, and with my enthusiasm, we even did a small pilot project on stem cells. But however, I got to know that stem cells is mainly an application to research. So for example, for any building to be built, you need first a platform. So I felt like, why don't I learn more basic science at this point and then move on to application later in my life? Because it's always the same concepts you apply in different cell types or tissues. So that is the maturity I gained. And one of the best thing I learned from her, or the best thing I remember throughout my life, is having a lot of technical skills doesn't make you a scientist.
True.
You should have an idea, and the idea should be able, like you should be able to present the idea as well as write it. That's how you can like get grants and publications. If not, whatever you do is of no use.
Absolutely.
So that's one thing I wanted to develop during my PhD. And because her research mainly focused on cardiac, so that's where I started my cardiac thing. And I did forget to say something else. So with the same stem cell passion, I worked on induced pluripotent stem cells in the first rotation of my master's, where we differentiated into cardiac myocytes. So from that step onwards, like cardiac has been part of my career.
Right.
And my master's thesis, where I did under the mitochondrial person, had a great impact on my life. And from then, rather than being termed as a stem cell person, I had a great love towards mitochondria. And all my PhD, my work is mainly focused on mitochondria, but it is more oriented towards cardiac.
Great.
So yeah, so that was the moment where I transitioned from stem cells to cardiac, and in cardiac specifically on mitochondria.
Andrea. It is fascinating. It is absolutely fascinating. I mean, mind blowing. I mean, I think you were focused at very, very young age. You knew what you wanted to do. That is something, at least you got that idea, and you wanted to pursue it, and you were very persistent, I must say, because it's just a story now. In 3 lines, you were finishing, but I mean, it's journey of years and perseverance. Really.
Yeah, I was always fortunate, I would say. Like, I got really amazing mentors. So if I had a faculty of 50 or more in my dental school, I had at least 5 to 10 people who were constantly supporting me irrespective of the issues I faced. So that was really helpful, I would say. And once after my graduation from the dental school, my patients did help me a lot. So, because if I was not financially well supported, I don't have the free hand to do academic research.
Correct.
And I feel this is very much needed, because at one point or the time, right, like I am right now 34, where I have a family now, recently have a baby. There are a lot of financial responsibilities.
True.
And another example I can give is my friends, undergrad friends. I'm in a batch of 100. I'm the only one who did a PhD from my undergrad. And most of my friends who have traveled to US are dentists. So all of us started masters at the same time. And in 2 years, all of us completed, and they moved to the dental school. They graduated in 2 years, and it took me 6.5 years for me to graduate from my PhD. So by the time I graduate, they make like 4 times my postdoc salary. Yeah, it is financially challenging, I would say. And another thing I can compare with my fellow PhD mates who started working in a company same time, they make twice my salary. So it is very, very less rewarding in a academic situation. But however, if you really want to strive for success, yes. And that's why I say I'm more fortunate, because I was not gone into any of the financial struggles till date, so that it made me go through, I would say. If I had that, probably I might have ended in a different situation, which would change my complete direction. And another main thing I have inherent, which keeps me always stay in academics, is I faced a lot of mockery, like, you don't gain money. Why do you want to do research? What's the use of doing it? So it's going to be the same thing if some other student is having a similar passion to go through. So unless until I see myself as an academic professor where I can train a PhD, I don't call myself success. And I want to wait till that stage. And I want to keep trying, because if I have a failure, the new one is again going to get the same mockery. Now they're at least saying that, okay, there is a student who has gone through a lot of stress, and he has paved a path in a direction where you guys can travel. But yeah, it's challenging, definitely. But at least you would have one story where they can show out, rather than a failure who just changed the stream with the situation. So yeah, that is the reason I'm more focused, I would say. And I'm still trying to sustain in the academic research at this point. Yeah.
No, I'm sure.
Yeah, that keeps me motivating every day.
Sure. I mean, the kind of I understand from where your passion is coming, so I can relate very well. And certain things, which is like you said, certain things is not, everything is not about money in life. So, but yes, that is a practical thing which you have very well said, that since you didn't face any financial troubles by God's grace, so you could pursue what you wanted. So might not be that everybody is so privileged, but then still, I think it is a very difficult thing to make a complete transition, and because we have so much of social pressure as well around us. So that is something which is very, very inspiring to understand from you. So Dr. Satvik, can you tell us or describe about your research interests and specific questions at this point that you are trying to address through your cardiovascular research?
So, in my PhD, I was trained mainly on Duchenne Muscular Dystrophy, which is one of the severe form of muscular dystrophy, which affects like almost all the skeletal muscles.
Right.
However, and the cardiac muscle. However, our focus was mainly on the cardiac myopathy that was created, and it mainly affects males. It's a and I wanted. So my boss has already found out a gene called sarcolipin that regulates calcium. So in Duchenne muscular dystrophy, there is a lot of calcium dysregulation. So therefore, my focus was on how mitochondrial metabolism or mitochondrial calcium or how mitochondria are affected in this specific disease phenotype, and how by knocking the regulatory protein, which my boss found it interesting, is going to ameliorate the cardiac myopathy. So I gained a lot of techniques during my PhD, I would say. I learned mouse echocardiography, where I literally can find out the cardiac function of the mouse. So we even learned isolating cardiac myocytes from the mouse heart, and then perform various cell experiments. And apart from this, I can isolate mitochondria from the myocytes or from the heart, and then do some functional assays in order to determine the metabolism of the mitochondria. So how do they have like what kind of metabolism they do have, and how functional are the mitochondria? So there are a lot of imaging techniques, like you can do the traditional way, like electron microscopy, where you can see the structure of the mitochondria, or else you can do functional assays where the mitochondria, are they intact, are they like already having good membrane potential using various confocal techniques. So I have learned all these techniques, and we found that the mitochondrial function is greatly disturbed in the Duchenne, and knocking down the calcium regulatory protein has greatly improved the function. So this is most of my thesis, and based on this, I moved on to another cardiac lab in the same department, where they work mainly on transcription factors such as YAP, which is a well-known transcription factor. So we are, and this lab has recently found the upstream regulators for this particular protein. And now again, we are focusing on metabolism, how it is being altered. Okay. So I'm going to apply most of my techniques in this particular disease model, where we focus mainly on pressure overload as well as volume overload by doing on various surgeries in the mice.
Great.
Yeah. So that is one thing I wanted to learn during my postdoc, is learning surgeries, if I could get, so that because I have some surgical hand from dentistry, maybe I thought like it would be a little bit easier for me to get that feather touch. Yeah. So that's one thing I wanted to learn during my postdoc. And other than the, yeah. Go ahead.
So I would like to, because your work is very fascinating, and I understand that you need to have a very dedicated approach in designing experiments. So how do you approach designing experiments and interpreting results in your research? If you can just highlight that, because I think that this kind of information will be really helpful for people who would be listening to this, who have joined us now, or who would be listening to this later on as well.
So the thing mainly about designing experiments, I would say everything is based on the research question you have. For example, I mentioned was metabolism. So what are the various kinds of metabolism that happened in a cell? So cell mainly has two types of metabolism. One is the cytosolic, where glycolysis. So most of the things come from biochemistry we learned in the second year in BDS, I would say, or first year. I don't remember. So yeah, glycolysis is one thing, and other one is mitochondrial metabolism, which is the end point for ATP generation or the energy generation. And earlier we used to think that where does oxygen get utilized? It is only in the mitochondria and to a little extent in the peroxisome where it gets utilized.
Correct.
So that is the reason most of my research. So I have to design in such a way which kind of metabolism is affected. Is it glycolysis? Then what I do is there are some limiting enzymes or proteins that can determine the process. So you either check for their protein expression using Western blotting, or you can even do for transcriptional analysis using real-time PCR or qPCR, quantitative PCR. So the thing with these is I would prefer doing translational, because genes can be transcribed or mRNA can be synthesized, but how many are being translated as proteins is more important.
Yes.
So that is the reason traditionally Westerns are the best, I would say. And it depends on the antibodies. If you want to do a lot, you can do ELISA, which is also a similar type of Western, but in a more fancier method, I would say. And these are traditional techniques. And earlier I mentioned, if I wanted to know how is the structure of the mitochondria. So mitochondria, where do they have the ETC or electron transport? It's on the cristae, which is the inner mitochondrial membrane, which folds into the matrix. So you can actually technically see the cristae of the mitochondria using EM imaging or electron microscopic imaging. So that will give us an idea how many number of mitochondria are there for that particular field. So we count individual mitochondria and we also calculate the area. In that way, we can determine are they huge, and we also calculate the aspect ratio, the length versus the breadth. In that way, it gives us the. So, for example, if the aspect ratio is close to 1, it determines that mitochondria are more round in shape, and the area determines the size, like are they big or small. So usually tubular mitochondria or rectangular mitochondria, because it's a two-dimensional rectangle, but usually tubular in like 3D phenotype. So it states that mitochondria are pretty active and they have healthy metabolism going on. So if they are small, it means more kind of division of mitochondria happening. So there are things called fusion and fission events which regulate based on the amount of oxidative stress. So what are the factors which can create oxidative stress is increased metabolism or increased calcium. So if there is a lot of mitochondrial calcium, then also oxidative stress can be upregulated. So there are kits where you can use confocal imaging to track the amount of oxygen radicals that are being produced across the groups. So that will determine one entity. And for example, for a healthy mitochondria, negative membrane potential is highly needed for generation of ATP and for proper functioning of the mitochondria. So membrane potential also can be estimated using dyes. So based on those dyes using confocal, you can either isolate the mitochondria or you can even do it in cells. These are live dyes, so you need to use in live cells. So this is one interesting thing. And so these are multiple functionalities, modalities where we can do it. And apart from that, I know one more technique called seahorse metabolic profiling. The name sounds little tricky, but where we can use cells or isolated mitochondria, and we can determine how the mitochondrial respiration functions. So literally you can add in specific substrates. For example, if I'm using isolated mitochondria, I can add in like only pyruvate or malate, which are the entries into the Krebs cycle, in order to determine what kind of substrate is more utilized. And you also can add in fatty acids. In cardiac myocytes, fatty acids is one of the major driver for energy source. So you can add in fatty acid and see how is the entry being done. So you can determine based on different metabolites, and you can even inhibit the complex activities. So for example, the ATP is produced in one complex, the malate, or there are multiple complexes, complex 1, 2, 3, 4, and 5. So 5 is ATP generation. So you can inhibit that in order to determine that. And you can also inhibit complex 1, which will inhibit specific usage of a substrate. And you can also inhibit complex 2 where it inhibits that particular substrate usage. So it will determine which complex is showing a big difference or which is being impaired. So you can also use a Western in order to determine the expression levels.
Right.
And you can also determine the functionality of the complex.
It's very interesting. Very interesting.
In depth, there are, and you can even do it. So, for example, you don't have access to live cells or mitochondria. You have only frozen tissues. So there are complex activity assays which can be used using a basic plate reader for colorimetry. So you don't even need fluorescence. Basic colorimetry assay can be done. So intact mitochondria, the difference between a lysate, where you homogenize the tissue, frozen tissue, prepare fresh, and do the assay. Here, the complexes are active. But in isolated mitochondria, the mitochondria are healthy and active. So it gives you a lot of additional factors when you are doing for isolated mitochondria, I would say.
Correct.
Because the membrane potential is pretty integrated.
Yes.
So these are the additional things you learn from this. It is slightly expensive, but definitely it is a supportive evidence, whatever you found. So it will help to bolster your research hypothesis.
Fantastic. It is so amazing to know all these technologies that you are using, and you are taking this research forward. So the question is that what we understand that when it comes to research, it is more about collaborations, right? So, or partnerships. So what collaborations or partnerships do you have with other research organizations, and how have these collaborations, if there is any, have it helped you, or in rigor, or more reproducibility in your results? Is there something like this?
So at this point, I would say is because I'm still as a postdoc, usually the collaborations will be the PIs or the professors' collaborations. So I won't directly develop something. For example, the EM facility or the core facility, it is basically in the main campus. So it is part of the Rutgers, but still you have to go over there. That is kind of an internal collaboration. So, for example, earlier I mentioned I know how to isolate mitochondria. So I know additionally how to isolate mitochondrial associated membrane. So, for example, in a cardiac cell, there is an organelle called sarcoplasmic reticulum.
Yes.
So, which is mainly the calcium regulator in the cardiac cell.
Yes.
So, because it carries 70% of the calcium in mice. So it needs to release and reuptake for the contraction and relaxation of the cardiac cell. And in cardiac myocyte, the mitochondria and SR, they stay in close interaction. So this close interaction is called a MAM, or mitochondrial associated membrane.
Okay.
So I got expertise and I learned that technique during my Ph.D. And because of that technique, I was able to get a co-authorship on my chair's paper, like a paper from my chair's lab. So that's how also the internal collaborations happen. For example, I know echocardiography. So that is one of the reasons why my new lab wanted me in, because of my techniques. So my skills. So that it would be easy for them to do the experiment. So they need not rely on the other person.
Correct.
So these are internal collaborations. And professional collaborations, sometimes we get samples from other collaborators in order to test the techniques which we are aware of or which we have expertise in. So these are the main things that happen. And also the professor has collaborations for clinical samples.
Correct.
So we always try to correlate, for example, the transcription factor, which I said in the current lab. We also have verified it in human cardiac failure patients, where the protein was slightly down. That's when we go ahead and design specific genotypes for the mouse. So if it doesn't have a correlation, it should either be a mechanistic study or other thing is it should have some clinical correlation. So these are the things that are necessary. So usually when we go to American Heart Association, or like which is one of the main conference for cardiac people, so that's where we develop the professional network. For example, one person I came across during my PhD, I still maintain my contact. At one point, he even wanted me to come for an interview for my postdoc,
Right.
which he offered me few years before the COVID thing happened. So this is where we network, and you'll come across a lot of literature review during your development of a hypothesis. So
Correct.
at that point, you know who are the big shots in the field. Thereby, you'll get to know, like, okay, maybe I can approach them for a mouse line. For example, mouse line to develop a mouse line, it takes several months at least.
Yeah.
And at times, if it is already available, you can collaborate them. You can write down an email to them. So usually, if you don't have a lab, usually it's the PI through which you channelize through the collaborator, or you develop the collaboration. So similarly, that's how it happens.
Great.
Yeah.
I think you work in a very niche area of cardiovascular research. So, what were the challenges that you have faced, and how you could combat those challenges during your entire research journey? I know you are still in the process, but still you have come a long way. So, I think that would be very interesting point to understand from you.
Yeah. Technically, it takes a lot of time, I would say, for getting me a little bit expertise on the basic echocardiography. It took me like a couple of years initially. So I started learning it from a master's student who was applying for his med school in the same department. So he trained me. So he trained me for almost several months. And he used to be behind me, like, am I doing it in the right manner or not? And then I would compare my values with already published data, like how close am I?
Right.
So, and there are also now, everyone publishes in a YouTube where you can know how the technique is to analyze the data. And usually, a echocardiography machine, it is equivalent to a big grant. So it's going to be several $100,000. So the company even provides some tutorials where you can go back and forth in order to know it. So, but when I learned the technique, there were no tutorials or something, because this was back in 2018. But now I can strongly state that I can at least state, okay, whether the cardiac function is okay or not. But I'm not an expert, I would say, but at least in the basic findings, I'm able to do it, and irrespective of the mice line. I did it in aged mice. Apart from my Duchenne project, I even worked on myocardial infarction and cardiac aging. So I even did echo on 24-month mice, which is like pretty long survival for them. So yeah, over the time, I learned the things. And definitely, yes, if I would be able to learn the surgeries, I can say that I know more than 50% of the techniques needed for cardiac. At least I can strongly state that. So that's one thing I miss. So because my long-term goal is to have an independent lab in a good academic institute, and I want to move back is my long-term goal.
Okay.
Short-term as well as long-term, because I need to first complete my 3 to 4 year postdoc so that I get qualified for the fellowships over there. So yeah, that is my thing. So unless until you are having
You're very focused. that is one impression we all are getting. You're very focused from day one. So so Dr. Satvik, one thing because just like clinical practice, still I think there are some scope of gaps, but I think with research, a lot of responsibilities comes, particularly when it comes to balancing things. So how do you actually balance your work life balance, maybe, if I just put it that way? How do you manage that?
So like healthcare itself, you need a lot of sacrifice, which many of the non-healthcare professionals don't understand, especially even the parents. So you sacrifice a lot of your personal space.
Absolutely.
That's how you can dedicate longer. For example, uh, I joined a new lab last November as soon as I defended my thesis. So it's technically new, and I had a baby in February. So other than the 5 days in the hospital, I hardly took a long break. And even after my PhD defense, I didn't take a break technically. So at times, and I can't, and you need, for example, my wife, you have a lot of issues during the first and second trimesters, I would say.
Yes. Yes.
But however, that was when I'm wrapping up my thesis, and I was going through a lot of stress. So I literally didn't give her even sufficient support. Instead, she was trying to ease my stress.
So sweet.
So I was fortunate to have such people in life, but definitely, yeah, I couldn't give a lot of attention when needed. But that's how research goes ahead, I would say. Yeah, like on Monday, I had this mitochondrial isolation experiment where after that, I do the essays. So literally, it was like 1:30 in the morning when I finished. I started around 9:30, 10 a.m. and it ends. And for the MAM isolation, I said it's a 15 to 16-hour protocol. So it's more like an overshift, which we do it. So yeah, definitely, if you're really passionate about something, yeah, it just goes through. But definitely, you need a lot of family support as well as mentor support.
Absolutely.
For example, my old mentor, he was always behind me, like, yeah, and he keeps me motivated. He works on the bench as well as he writes the grants. So it takes a lot of time to focus on a grant, but simultaneously, he also helps me out with few of the minor stuff in the lab so that he gives me a helping hand. So these things always keep me motivated, I would say. And yeah, another reason because maybe I forgot to mention it. The reason I chose research is not because I can't do clinics or I don't like clinics. I was good at clinics, but if everyone is doing clinics, who the hell is going to do research is my question. And I thought like,
you are speaking my mind. Exactly.
So my thought process is like, for example, a clinician is there. Maybe if he deals like 10 cases per day, and over a month, even if he takes 5 days off, it's 250 cases a month. Technically, for 12 months, it's going to be 3,000 cases. Even if he attended camps, maybe another something, 5,000. And over 10 years, he may maximum go across like 50,000 cases. But the research question, which I might be focusing on, might reach to a broader people. It's not possible that every research will become a big drug, but it will definitely answer some other question which is already established in the field. Absolutely. And it might help in moving a step ahead. For example, one funny thing I faced or I saw over the social media during COVID. So they thanked the frontline defenders. They thanked the policemen who helped out. They thanked even the pharmacists. They thanked everyone else, teachers, everyone who participated. But none of them thanked a scientist or a researcher. One thing I would like to say, not all pharmacists, just because a pharma company develops a drug, it doesn't mean that pharmacists are the ones who does the drug thing.
True.
So which is completely a misunderstanding in the public, I would say. Like there are a lot of MSc grads, there are a lot of PhDs who are mainly involved. If not, COVID would not have been restricted this better. And I felt like the world has understood what research is and how essential it is. Yeah, doctor gets the best satisfaction. Clinically, I had a lot of satisfaction during my undergrad because when patient says, yeah, happy, the smile you see at the end of the day or the pain they are relieved from gives the immense satisfaction. But research doesn't give that. It's not a reward that is being given right away. It takes ages, at times decades, or at times a lifetime, I would say. but you need a lot of patience.
Yeah. Yeah.
And the maturity I gained over the time. Initially, when I came in, I thought like, oh, I did a BDS, like freaking 5 years. I did it. Oh, I have attained a lot of patience, and I even can troubleshoot the diseases.
Mm-hmm.
Yes, troubleshooting will help because differential diagnosis is nothing but troubleshooting in experiments.
Exactly.
But the patience you developed is nothing for a PhD. The amount of patience required for a PhD is, if you are being forced to read the same BDS 2 or 3 times, the amount of patience you get, that's the amount of patience required for a PhD. Then I thought like the top-notch person is going to be an MD PhD or a physician scientist, and then comes the scientist, and then only comes the doctors.
Correct.
If there was no penicillin, there is no doctor who's going to treat.
Absolutely. Very true.
Hopefully, yeah, if it was more rewarding, it would definitely increase the students' perception or students' interest. Because see, at the end of the day, if the financial needs or responsibilities are not met, you can't focus properly. If I had an issue in my house, I can't focus more on my research, because if I can't focus more, I can't do my experiment properly, which involves a lot of money and effort. And I have to spend each and every penny carefully, because this is nothing but the taxpayers' money. That's how we get the funding from. So, yeah. So these are the things which I always think of. And the interest of the physicians towards research also should be changed. It is not that easy. They think, like, which I thought earlier, like research is easy, but research is not easy. It requires even more lot of patience and time and effort and sacrifice, definitely, yes. And it's not even you get the satisfaction right away. Yeah, it at times costs a lifetime.
So, Dr. Satvik, can you describe a particular exciting or promising finding till now from your whole cardiovascular research, and what are the future implications of this particular work that you are doing? So, if there is something you can share, it will be very nice.
So, because the postdoc I started, it's completely new. I can't say much about it, but my PhD work, it will definitely, for example, my boss already found this particular protein, which called sarcoplasmin. He did various gene knockouts in a Duchenne muscular dystrophy, where that particular severe model mice, it survives only 2 to 3 months or 4 months. After knocking down that particular protein using genetic ablation, it survived more than a year and a half. So that's a significant increase in the survival. He also used AAV9 approach, where he is using adeno-associated virus in order to knock down the protein, or knock down the transcription, so that doesn't get translated, right? So even in that approach, he was able to succeed. And it could, because it regulates the SR calcium regulation, it provided a great improvement. But the thing is, even the mitochondrial, so my question was, even the mitochondria, are they functionally enhanced, or are they in a better situation compared to the phenotype? And that's where my answer comes in, and we have shown that it has significantly improved the function of the mitochondria as well. So now the thing is, you have to find small molecules. It takes several decades, and the NIH or any funding agency, they like more about fascinating ideas. They don't usually go for simple questions. So unless until you get paid, you can't support the lab, right? You have to pay for the salary, you have to pay for the resources, a lot of things. Correct. So yeah, the amount of work we have done can be translated, but not sure when it can be translated. It's gonna take a long time to get translated. So in my focus, it is pretty promising and interesting. But however, yeah, we don't know whether it can really get translated right now or several years later, or not at all get translated. Because everything we see in mouse might not be going to human trials. So maybe you have to next check for higher mammals such as rabbits or dogs.
Right.
and kind of need higher grants. So you need special skills also to maintain them. So yeah, it's a different set. So that's what there are n number of stages which people are not aware of that goes through. So yeah, that's why I was saying earlier, the reward you get at the end of the day, yeah, publication is a little bit satisfactory, but if it gets translated, that's the top notch, I would
Yes,
say.
absolutely. So, coming to the concluding part of our talk. So, finally, I mean, you have given the width, breadth, depth, length, everything. So, what would be your advice to somebody who is, interested in getting into research? So, let's say whether from dentistry or maybe from any other field, from any life sciences field. So, what would be your advice to these aspiring people?
See, everything, as I mentioned earlier, it's mainly the situation that determines what you want to do. For example, in dentistry, like there are many people who are forced to get an admit just because you want a doctorate in the doctor in the family,
Yeah.
something like that. And later they might not be interested in doing the clinics.
Correct.
So for them, this could be an alternative route, but choose it wisely. I would say it requires a lot of dedication and hard work. So yeah, you have to put in even more effort than that. Yeah, few might find it interesting because few people have difficulty in handling mice. They prefer doing only cell culture experiments. Yeah, few labs do cell cultures where you can find that. But yeah, it would always be good thing. And other thing, yeah, late night shift works will be there. And I would say research is never a 9 to 5 job. It's more like you have to put in your personal effort then only. And financially, it's challenging. It's very, very less rewarding than dentistry, I would say. So, for example, if you're an MSc grad or a PhD, the only option you have is research. For us, at least we have another option, clinics, where we can think of that. Like we have multiple branches. But if you are interested in research, yeah, it definitely has a lot of effort and time you need to invest. But if you are prepared for it, yes, this would be a wonderful profession. See, there is. I usually watch a lot of movies. So in Three Idiots, you have the middle one, right? Madhavan in the original one. Yeah, he would say if he had done the wildlife photography, he might have a small car or a small house and little slow growth, but he has a satisfaction in life.
Yes.
So if you are really having that satisfaction with research, then yes, do it what not it is. I don't demine someone who is doing an industry. Yes, even that is also dedicated to research. Yeah, better salary, better life. Yeah, definitely better than an academic researcher, I would say. So it's your choice what you want. For me, my end goal was to become a PI, to have my own lab and train. And recently, another factor added in when I want to go back to India, I want to even take a dental grad who is really interested in research because I spoke to a few on the LinkedIn. They said like I'm really happy seeing your profile. So they faced some mocking during because they moved to masters for a different profession and they were asked, why are you doing this kind of? See, that's the diversity we lack and not everyone is open to it. And I hope the trend is changing a little bit and soon it will change. So this is the diversity I get it here in US. So maybe I want to be the change, I would say, like bring that change back in India. And another last thing I would end, I did cardiac research doesn't mean I don't want to leave my oral biology. My end goal is to do the orocardio link. So where it is going to be multidisciplinary. Yes. And that's where I want to prove myself slightly different. It would help me out in answering. So whatever I learned here, the techniques could be advanced.
Yes.
So I can always apply back in oral biology targeting the diseases. It takes maybe a couple of years for me to brush up the literature, what is going on present. So yeah, these are the things I have in mind. But definitely, yeah, if you're the three things to become a good researcher, I would say the ability to question, if you have that kind of integrating questioning, like, okay, what's this? Why should be this done? And you have the patience to test it.
Yes.
Patience is one of the key factor. So, for example, you get an answer today, like your experiment worked. You can't leave it. You have to repeat the same experiment 3 to 4 times to say that, yes, this is an S.
Exactly.
If it's a failure, you have to again repeat it 3 times to prove that it's a failure. That's how research is. So these are the 2 things. And for dentists, you learn a lot of differential diagnosis. It is like multi-modality thinking, or thinking in multiple directions. Okay, if you see a white lesion, what all it could be? Could it be a leukoplakia lesion, or could it be a simple candida lesion, or it has multiple white lesions? So how you differently think about, like, okay, what would be the factors? Similarly, in an experiment, if something doesn't work, what are the things which I would have made wrong? So this is equivalent to troubleshooting and research. So that is already inherent as a dental student, I would say. So patience also you developed a lot compared to any other grad student, because dealing good patients and bad patients, I won't say bad, uncooperative patients, you still have to deal them. So in that way, it will increase your patience. And yes, for example, you have prepared a denture which breaks on the day of insertion due to the unusual thing. So that's where you develop patience.
Yes.
So, or you are polishing your final denture and it breaks. Then you have to repeat the all step. You have to please your patient to come multiple times again. So this is over time you gain the patience, but this is not just sufficient. You need even more, I would say. So yeah, but these possibilities will make you a little bit easier for you in research, but definitely, yeah, effort is also needed. And you have to be patiently waiting for the result. At times it comes in a day. For example, cloning. You want to do a small bacterial clone. At times it works in a day. At times it takes several weeks. So yeah, or months, I would say.
Yes. Thank you, Dr. Satvik. It was wonderful talking to you, and I hope this session has enlightened the young minds and anybody who has been watching this. I think it was really awe-inspiring, and I enjoyed thoroughly, and I'm sure our audience enjoyed it too. Thank you so much for being here once again, and I think we will meet in future with many such conversations. So thank you.
And thanks for inviting on this platform.
Thank